All right, our numbers are leveling off, so I'm going to recommend that we go ahead and get started. So welcome everyone to our last seminar of the term. It's my pleasure to introduce our speaker, Professor Caitlin Casey. So Caitlin earned her PhD from Cambridge in the UK, where she first started working on characterizing ultraluminous infrared galaxies, WERLS, a topic she's really continued to work on ever since. She then moved from one institute of astronomy to another, transitioning from Cambridge, IOA to the Hawaii IOA as a Hubble Fellow. After moving to Irvine, UC Irvine for a few years as a MUQ Fellow, she joined the faculty at UT Austin, where she's been since. So Caitlin's won many awards over the years, including most recently the Newton-Lacey Pierce Prize from the AAS, which is awarded each year to recognize outstanding achievement in observational astronomy for young faculty members. And I want to mention also that Caitlin's an award-winning educator. She's won the College of Natural Science Teaching Excellence Award at UT, as well as the Cottrell Scholar Award in 2019 and 2020, respectively. So Caitlin's an expert in galaxy formation and evolution. She's really been a leader, particularly in the study of massive, rapidly star-forming dusty galaxies, high redshifts. And she's used really any telescope that you can think of on the ground or in space. So Herschel, Hubble, Spitzer, Sophia, Scuba-2, Keck, and ALMA. And she's heavily involved in early JWST programs, which we'll hear more about today. So Caitlin's happy to field questions as we go, so feel free to raise your hand or pop your question in the chat. I'll keep an eye on that as we go. So without further ado, Caitlin Casey, welcome, and take it away.
Great. Thank you so much, Jordan. It's awesome to be here. I, of course, wish I could visit in person, but such are the times. I know we're almost there, but not quite yet. Today, I want to talk to you about the rarest galaxies in the first 2 billion years of the universe's history. There's been a lot of rapid development in this subfield in the past several years, and there stand to be many more rapid developments as JWST turns online. Of course, the high redshift universe is one of the major goals of JWST science. And so we hope to see a lot of advances in the next several years. So today I'm going to split the talk in half a little bit, weighted a bit more towards data that already exists. But I want to talk about some of the huge strides that have been made using these two groundbreaking facilities, the Atacama Large Millimeter Array, surveying the sky at millimeter wavelengths, and of course JWST, which will operate in the near infrared and is already operating. We just haven't yet had the pleasure of seeing some of the data. And the intersection of these two great telescopes really is hammered home in the high redshift universe. This is a plot that I'm sure you've seen many times, the star formation rate density of the universe. So star formation formed per unit volume as a function of time. This plot is a bit different than probably the typical version that you've seen, because it splits the contributions into unobscured and obscured portions. So direct rest frame ultraviolet light from young hot stars, that contribution is shown in blue, and it is much lower overall than the contribution that is absorbed by dust and re-radiated at long wavelengths, at least out to redshift 2, the peak of cosmic star formation. But what you'll see is, although our surveys of the UV, rest frame UV universe have extended well beyond, the middle ages of the universe towards the high redshift universe, out to redshift 11 or so, and those are mostly pencil beam surveys from Hubble Space Telescope, and some, very wide field surveys from the ground looking for rare Lyman break galaxies. The obscured component has not kept pace, and we have very loose constraints on the total star formation rate density of the universe, reprocessed by dust, beyond a redshift of 3 or so. So in those first few billion years. So ALMA has really been quite useful in focusing and honing in on this epoch, trying to understand what we're missing of obscured star formation at early times. That has very interesting implications for the formation of dust, also the formation of massive halos, because these dusty, luminous galaxies tend to be very massive. And then, of course, JWST will push everything further, the redshift horizon, further beyond what we have from Hubble Space Telescope, answering questions like, do massive galaxies play a role also in the reionization of the universe, and how clustered these systems are? These are questions that we just cannot answer with existing Hubble data or existing wide field ground-based data. You really need the ensemble of these two facilities to answer these big questions. Just to give you a taste of some of the really groundbreaking discoveries that have been in the high redshift universe from ALMA over the past several years, if you don't follow this closely, we have resolved ISM kinematics within high redshift galaxies on very detailed scales, looking at a bit over the scale of giant molecular clouds at redshift of 4, thanks to the aid of gravitational lensing. We think we can also resolve dark matter substructure using ALMA to resolve background lenses. We've detected tidal tails in mergers at redshift greater than 4. That's not possible to do through starlight due to surface brightness dimming, but thanks to the negative K correction, we can see it in dust emission. We've measured molecular outflows at redshift of 5, and that is really remarkable. This has not been done very well at lower redshifts, but thanks to the frequencies that ALMA covers and its sensitivity, we can see this at redshift of 5. We've detected galaxies that lack absorption almost at every other wavelength. We detect them through absorbers along line of sight to like high redshift quasars, and we can finally detect those in gas emission thanks to ALMA. We've confirmed some of the most massive dusty star forming galaxies, or DSFGs, at redshift out to 7. That's really remarkable because we have something like 1 billion solar masses of dust formed in just 800 million years after the Big Bang. That poses really interesting questions for how dust itself is formed so quickly after the Big Bang. ALMA has also revealed spiral arms and bars, like very detailed morphological structure in galaxies at redshift 2 to 4. And last but not least, and this is kind of where things are going with the ensemble of JWST and ALMA together, is that ALMA has been rather unpredictably, I would say, before it was turned on, ALMA has been really crucial to the spectroscopic confirmation of very high redshift galaxy candidates. The highest redshift spectroscopic confirmation that exists, not from ALMA in particular, but across any facility, was confirmed through the 0388 micron line detected by ALMA at redshift 9.1. So it's a really powerful tool in the high redshift universe. Oh, and there's also that tentative detection of a redshift 13 line reported just a couple of months ago. I didn't include that on the slide, but this is really a powerful facility. So ALMA really has been transformative for individual discoveries, bringing us into different parameter space of thinking about high redshift galaxies. But one big question that I've been trying to focus on is how can we push our aggregate knowledge of obscured galaxies as a whole, understand their volume density, their role in cosmic star formation. How can we do that at a population level rather than revealing very interesting physical features on a case-by-case basis? So of course, this field of galaxy evolution of the high redshift universe really was launched, many years ago when ultra deep fields period, but also the Hubble ultra deep field was imaged for the first time, and it revealed, thousands of galaxies packed in a small area of sky, and that from that simple image, you can derive so much science. You can really study the evolution of galaxies over cosmic time, and in many different ways, dividing galaxies by different types, etc. So a natural thing to do when ALMA, this remarkably sensitive telescope, turned on, is to do a similar survey over a similar amount of area. Maybe we would see thousands of galaxies in their dust emission. So that was, one hypothesis before the first ALMA deep field was completed. But what you see is something that's very different. So on the left, we have the HUDF with something like 10,000 galaxies. And on the right, we have the ALMA map of the HUDF taken from the ASPEX program, which is one of the first large programs launched by ALMA in extragalactic work. And what you see is 35 galaxies. It's pretty sparse. And so this led to, several papers in the literature claiming, that the early universe must be rather devoid of dust. We see this, striking contrast where we just see very few sources in dust emission. So why are there so few dusty galaxies? Are early universe galaxies devoid of dust? Or are we looking in the wrong places? Is this, something that's abnormal or unexpected? And this is propagated to the star formation rate density plots that maybe you're more used to seeing. And this is also making an attempt to split up the obscured and unobscured components. And what you see in the early universe beyond a redshift of 6 is that the total star formation rate density contribution from these different papers really converge, and the dust contribution to the total is relatively small. Therefore, the thought is that highly obscured galaxies contribute very little to the total star formation rate density. However, this lacks a more nuanced view of the situation, primarily the very important fact that dust will preferentially live in high mass galaxies. There is more dust in high mass galaxies, and that dust is more efficient given the geometry of those high redshift galaxies, such that it obscures ongoing star formation more effectively. So this plot is from Kate Whitaker's 2017 paper, in which we showed that as a function of stellar mass, the fraction of star formation that is obscured by dust increases quite a bit, such that at a stellar mass of 10 to the 11, which is, substantially high, you have something like 95% to 100% of all star formation would be emitted at long wavelengths and reprocessed by dust. This is showing the same thing in a slightly different way, the star formation stellar mass relation, or the main sequence of galaxies. And you can see the star formation rates where the relative contribution from unobscured emission in blue and obscured emission in red. And you can see at the high mass end, almost all of the emission is coming out at long wavelengths. So it's highly obscured. And you put these things together, and also an understanding of galaxy luminosity functions, and you come up with a schematic that looks something like this. If we look at unobscured galaxy populations like Lyman break galaxies, the luminosity function has a very steep faint end slope. So there are a lot of very faint galaxies. And then there's a Schechter exponential fall off at the bright end. And dusty galaxies are far more rare, roughly a factor of 100 times more rare than Lyman break galaxies, but their total star formation rates are much higher. The faint end of the IR luminosity function is much more shallow because these galaxies at certain star formation rates are just outputting much more at UV wavelengths, unobscured than obscured. And so the result of all of this is that when you have pencil beam surveys, when you're looking on a few arc-minute scales on the sky and going very, very deep, you will not see intrinsically rare galaxies that may only constitute 1 in 100 relative to more common Lyman break galaxy types. So these star formation rate density plots don't really tell us that galaxies are less dusty at high redshift. They instead tell us that there's a perceived absence of very rare extreme dusty galaxies at redshift greater than 4 or so. This is the same type of galaxy that actually dominates cosmic star formation at redshift 2. If you break down the contribution to the star formation rate density at redshift 2 where it peaks, something like 50% will be locked up in extremely IR luminous, massive star forming galaxies. And there is an absence or a perceived absence of those at earlier times. But what I'll argue today is that actually we've done a pretty bad job of searching for those rare luminous sources. And you can think of rare dusty galaxies as akin to rare quasars. We're not searching Hubble Ultra Deep Field for the highest redshift quasar. So why would we do that with rare dusty galaxies? Instead, of course, you use all sky surveys to try to find rare quasars. And so that same approach is needed for extremely obscured systems. And of course, we do know that there are extremely obscured systems out, at least to redshift 7, as discovered by the South Pole Telescope, which consequently is doing a very wide field search for these, but happens to be sensitive to gravitationally lensed systems. And there is the hypothesis, actually, that dusty star-forming galaxies are more intrinsically massive often than quasar host galaxies, and they're also on for longer. They have a longer duty cycle. So they can really be a very useful probe of rare galaxies that test the limits of Lambda-CDM. We also have no idea how their dust formed so quickly after the Big Bang. This is just an illustrative example of a paper that dove into, the mechanics of actually forming something like 1 billion solar masses of dust in less than a gigayear after the Big Bang. And, the best models don't quite come close to what we've actually observed in the early universe. So what my goal has been is to try to find more of these. And in theory, finding very high redshift obscured galaxies is where submillimeter surveys really shine. And this dates back to the first submillimeter surveys done by instruments like SCUBA right before the turn of the millennium. So in 1998, that's a figure from David Hughes's paper. But just to illustrate the point here, I have a spectral energy distribution of a galaxy, pushing it back in redshift. So it has fixed luminosity. And I show you the observed flux density on the right here as a function of redshift at 3 different wavelengths at 1 millimeter, 4 microns, and 9,000 angstroms. So in the optical, near infrared, and millimeter. And what you see, predictably, the optical near infrared light drops like a rock at high redshift. Things get fainter as they're further away. But because of the unique shape of dust emission, it's black body emission in galaxies, and the fact that we're actually looking at the Rayleigh genes side of black body emission, you see this really interesting effect that the flux density as a function of redshift in the millimeter is pretty much flat. And that is what we refer to as the very negative K correction in the millimeter that makes a redshift 10, redshift 12 galaxy just as easy to detect as a redshift 1 galaxy. So if they're there, you don't have to go super deep to find them. So my quick summary of the last 25 years of trying to do this, some millimeter surveys have been trying, is that, we're just really lousy at getting redshifts for galaxies. And it turns out they matter a lot, and doing precision work really matters. Just to show you some examples from my own work, where I thought I had a redshift identification for a given galaxy, but then ALMA follow-up subsequently revealed that the position of the submillimeter emission was slightly offset from what we thought, we nailed down as the sure counterpart of the submillimeter emission. And often, it takes decades to spectroscopically confirm these sources. On the right, I show an example where we had what we thought was a very good redshift for a submillimeter galaxy at redshift 1.1. Turns out we accidentally, serendipitously discovered that through our ALMA programs that the redshift was 4.6. And those levels of misidentification, you may think don't matter, but actually every single one contributes a lot of confusion to our understanding of the redshift greater than 4 obscured universe. So misidentifications, even at the 5% level amongst a population, can wash out all high redshift constraints on the star formation rate density. So with this, I want you to consider 2 hypothetical universes, one in which the very early universe is quite dust poor. By that, I mean there is a extreme rarity of very luminous IR bright sources. So it's not really saying about anything about the dust content in individual galaxies, just rather about the volume density of very luminous IR bright sources. And then alternatively, consider a dust-rich universe where there's a population of extreme IR luminous sources that we just haven't been good at finding, and they happen to dominate all of cosmic star formation, even out to high redshifts. And these 2 hypothetical universes are meant to be a bit provocative. I think if you speak to a normal rest frame UV OIR astronomer, they would tell you certainly, the constraints on the universe indicate that the dust poor universe is much more feasible. But what I want to argue today is that actually, and there are literature sources that argue either way, the differences between these even dramatically different universes results in, a given sample of submillimeter galaxies, whether 3% or 7% of those systems sit beyond a redshift of 4. So you can see the level of precision that you need on characterizing a population in order to get that high redshift needle in a haystack population just right. And so a couple of years ago, we set out with this goal to, come up with a strategy to more efficiently identify what the obscured contribution to cosmic star formation is, particularly beyond a redshift of 4. And so we launched this survey called Mapping Obscuration to Reionization with ALMA, MORA. And it is a alternate type of ALMA deep field. It's a 2 millimeter deep field. This is roughly the size of candles. If you know that survey, it's one of the HST wider field surveys that have been done. And so this is roughly the size of that in the middle of the cosmos field. And so I'll highlight work today from Jorge Zavala and Sinclair Manning, my former postdoc and student, respectively, on the MORA survey. And just to give you an idea with respect to other ALMA deep fields, these are shown to scale. So MORA really is quite large. It's the largest in comparison to extragalactic deep fields. And yet it only costs the observatory 15 hours. And you might figure out quite quickly it's because it's not actually super deep, but that is not the most important aspect of the survey. So why would we do this survey at 2 millimeters? 2 millimeters is very useful for filtering out the low redshift universe. And so here I'm highlighting with the red line, the thick red line, the flux density of an object of a fixed luminosity as a function of redshift. And you can see it takes this bizarre dip. So that means that, a given luminosity object is fainter at redshift 1 than it is at redshift 7 at 2 millimeters. And so if we tune our survey sensitivity just right, not too deep, then we can actually filter out low redshift sources and catch the high redshift tail of the population. And so that was the goal of the survey, is to just, even in a very simple understanding of the population that is detected in a 2 millimeter map, infer the total contribution to cosmic star formation. So this is just a little schematic showing you, okay, if you tune to a very dust-rich universe all the way to a dust-poor universe in 4 different colors, that would result in a very different redshift distribution of the sources that we find in the map, and also the number of sources we find in the map, anywhere from around 8 sources in the map to over 50 in the map. And to show you what we found something more or less in the middle here. So we have constrained the redshifts of all of the detections. We found a total of 12 sources in this map. It has somewhat effectively constrained the model to be somewhere around the blue line here is what it's most consistent with. There are more details in here about the redshift distribution and how that can tell us interesting things about, dust geometry and whatnot, but I won't get into those details today. But what it has demonstrated, the MORA survey, is that 2 millimeters is a very effective strategy for selecting this high redshift tail. So 75% of these systems are above a redshift of 3 and 30% above a redshift of 4. That compares to 850 microns, where 5% is above redshift of 4. Just to show you what these objects look like, these are just showing you kind of descriptions and redshifts for what we have in the map. The first 3 columns here are deep imaging from Hubble, from the Candles survey, and you can see these sources are primarily undetected. And they are undetected often until you get to Spitzer. And so this is another reason we're very excited about JWST, is that we will actually have much deeper and high resolution maps from JWST to match the depth of what we're getting with ALMA. There's a follow-up paper, particularly for these sources that are still unconstrained. We don't have very good redshifts. They are what we call HST dark or OIR dark sources. And that is work done by my former grad student, Sinclair Manning, who's now a Hubble Fellow at University of Massachusetts. Yeah, and we think they are the progenitors of massive quiescent galaxies at redshifts of 2 to 3. We also have found in this map some really interesting sources, including Mambo 9, a funny name, but It sits at a redshift of 5.85. This is the highest redshift unlensed dusty star-forming galaxy that we know of. And because we have good constraints on the volume density of this survey, we can actually constrain the halo mass pretty well. It is kind of at that limit where it's testing Lambda-CDM itself. This is an incredibly dust-rich system. 96% of its baryonic matter is in gas and dust, and very little in starlight leaking out. And so we hope to find, many more of these sources, because we do have an extended MORA survey, which will hopefully be observed in the next 2 weeks with ALMA in cycle 8. Jorge Zavala is a former postdoc from my group, now NAOJ staff member, and he did a very cool joint analysis of deep ALMA 1 millimeter, 2 millimeter, and 3 millimeter data to constrain the very high redshift star formation rate density. What we learned from that is that 1 millimeter is just not constraining, so that, very deep aspects, ALMA deep field is very useful, for looking at redshift 1 to 3 galaxies, but that high redshift tail, it's just not sensitive to. And that shows you, like here, Jorge shows in gray a variety of models with very different IR luminosity functions at high redshift. They all fit the data quite well at 1 millimeter, but you see the variety spans out and quite a bit at 2 millimeters and at 3 millimeters. And so when you include the 2 and 3 millimeter data, those models really converge on one answer, which gives us the first real constraint on the IR luminosity function from redshift 4 to 7. And this is what Jorge found in terms of the star formation rate density. And what we're seeing here, the take-home message is that redshift like 4 to 5 marks this epoch where there is a transition from at earlier times a largely unobscured universe to one that is increasingly dominated by obscured galaxies. And so this is really marking the turn on of the most massive extreme galaxies. And so, another interesting comparison is if you take the integral of this, of the IR luminosity function, and look at the star formation rate density as a function of redshift, and the number density of galaxies, it mirrors rather well this black line, which is the number density of quasars in the universe. So we do see this close analogy between the quasar population and the dusty star-forming galaxy population. And so we need to think about these systems like quasars. We need to launch much wider field millimeter surveys to find them across a range of redshifts, because I think they do have very interesting constraining power that quasars alone can't give us. And so there are some efforts in the works to do this, primarily the Toltec instrument at the Large Millimeter Telescope in Mexico has plans to, of course, survey the sky at a variety of millimeter wavelengths that would make the selection of these systems much more routine. Okay, in the few minutes that I have left, I do want to share with you some of our plans with JWST. I didn't want to belabor the point on this because we just don't have the data yet, as you know, but I wanted to share some of the plans and also maybe discuss things that might be of interest to some of you. So I'm one of the PIs of the Cosmos Webb survey, which was the largest Cycle 1 program that was accepted. It is a treasury program. The data from Cosmos Webb will be public immediately once taken. And this survey is a bit different than other JWST deep fields, of which there are several. This is the largest, not just in time, but also in area of sky that is covered. So what I'm showing here is the Cosmos survey, which has been around since the early 2000s and was forged by a very large Hubble ACS mosaic and a single filter in I-band covering almost 2 square degrees. So that's what you see here is the Hubble data next to the size of the moon. And what we're doing with Cosmos Webb is we're covering this middle portion of the field. It's 0.6 square degrees. The blue area will be covered by NIRCam. It's contiguous. It's roughly a square that's 45 by 45 arc minutes. We will the 4 filters in NIRCam listed here. And then in the red areas, we will have MIRI coverage at 7.7 microns. It is not contiguous. And this one field out here exists because one of the fields didn't have a guide star. So we had to construct these kind of columns of MIRI coverage that will intersect quite a lot with the NIRCam mosaic. I just want to show you a bit of a simulation to give you a sense of scale of how large this is. So the background image shown here is the Hubble Ultra Deep Field as it is observed. I'll show you a simulation of what we'll see with JWST from the Deep Realistic Extragalactic Model, or the DREAM model. And this simulation was put together by Nicole Dracos and Bruno Villaseñor at UC Santa Cruz. So here's the Hubble Deep Field, and now transitioning to a simulated JWST deep field at the depth of Cosmos Webb. False color, of course, in the near infrared, and just zooming out beyond the scale of the HUDF. This line is roughly about 10 arc minutes across, and we continue to zoom out to see the scale of all of Cosmos Webb. And so that gives you a sense that this is about 200 times larger than the HUDF, but at HUDF type depths. Here's the scale of the moon. So it's roughly 3 full moons in size. So Cosmos Webb will image something like 1 million galaxies down to magnitudes roughly 28. In NIRCam, we expect to find about 32,000 of those in the MIRI coverage. It only covers 0.2 square degrees. One question you might have is, why so big? Why would you ever, want to cover this much area with JWST? And the primary goal is reionization era science. We think cosmological simulations tell us that the early universe is patchy. And so we want to understand the distribution of galaxies during the epoch of reionization. We think we'll find something like 5,000 galaxies from redshift 6 to 11 in Cosmos Webb. We also have science goals dedicated to quiescent galaxies at high redshifts, finding the first quiescent galaxies, and also observationally constraining the stellar mass to halo mass relation through weak lensing measurements. But I just want to dive in a little bit on this goal 1 and tell you a little bit more. So this is a cosmological simulation at a redshift of 7 in a delta Z slice of something like 0.5. And it shows you the distribution of galaxies shown in black here. These are all galaxies that we would detect with JWST. And the fatter points are more luminous in their rest frame UV. The blue patches are areas of neutral intergalactic medium, and pink is ionized intergalactic medium. So this is an epoch when the universe was actively, transitioning from a neutral universe to an ionized universe. And in this simulation, you see there are areas of the map that are highly clustered with massive galaxies on the scale of Cosmos Webb. And if you look at the other JWST deep fields that are planned, they're all roughly of this size that may very well miss these massive rare overdense peaks. And in terms of other ERS and Cycle 1 programs, they're a little bit bigger, but still arguably not big enough to capture large scale underdensities and overdensities themselves. So Cosmos Webb was really designed to eliminate cosmic variance completely on these at these redshifts. This is a cosmological simulation of the reionization process, a particularly beautiful one. And of course, reionization, we think we have a pretty good understanding of at least its midpoint, which is constrained by Planck to be redshift 7.7. Its ending around redshift 6 or so, but its beginnings are really unconstrained through observations. And there are also, quasar sightlines that suggest that the process could be very patchy, and there are examples of neutral IGM pockets existing down to redshift 5.5. Simulations suggest reionization is just a really patchy process on very large scales. There can be large scale bubbles in the IGM that are ionized, while there are other very large neutral regions. So other deep fields really don't capture this patchiness like Cosmos Webb will. Another question we will address with this JWST data is what galaxies drive reionization? Is it low mass galaxies or high mass galaxies? And the implications for those two hypotheses are a very different history of reionization itself. So if it's low mass galaxies, it's more of a slow ramp up and also spatially more coherent. If it's rare massive galaxies, it might get a quicker ramp up, but at later times, and be more patchy. Constraints from Planck aren't quite good enough to tell us which history it is, and so JWST will be really crucial for telling us this. Yeah, models do disagree, and there are various reasons for thinking one might be right or the other. Of course, measuring how it happened and tracing ionized bubbles themselves requires Lyman-alpha follow-up. Lyman-alpha, we think, is a very good tracer of ionized bubbles because neutral IGM will suppress Lyman-alpha as it resonantly scatters. And so we've launched a parallel survey to Cosmos Webb called the Webb Epoch of Reionization Lyman-alpha survey on Keck. This is a 29-night Keck key strategic mission support program for JWST, and it's ongoing. I actually just observed night before last for our last night of the season for WERLS, and we are targeting meticulously trying to gather spectra of any redshift 6 or greater candidate in these key fields that will be covered by JWST in order to understand whether or not they live in ionized regions of the IGM. Here's just a snapshot of the filter set of Cosmos Webb and how it compares to data that already exists in the field. So the gray bars are the depths as a function of wavelength of existing imaging. So we get quite deep in the optical down to 28 magnitudes already from Subaru data. This is the Hubble data here in I-band down to 27.5. But then the near infrared, of course, were much shallower. That's done from the ground. Spitzer is quite deep, but you see we go 2 magnitudes deeper with Cosmos Webb, and the deepest filter of all will be at 2.77 microns. And it will be an exquisite data set, and the MIRI data here is up at 7.7. We think the data set will be very useful to many people, and I hope you at McGill get to use it quite a bit as well to do your interesting science. Just a taste of some of the legacy science that we think could be done. Galaxy morphologies across a huge range, the data will have 0.0 arcsecond spatial resolution, which is, hard to believe. And we even get those rest frame morphologies in the near infrared from MIRI, slightly worse resolution, but not much. Spatially resolved SEDs for galaxies, understanding whether or not there's evolution in the dust attenuation law, and combining data sets with, for example, ALMA. We may, in this data set, identify black hole seed candidates from direct collapse black holes. That will be possible. They will have a very steep near infrared spectrum. We may gain really interesting insight to the supermassive black hole galaxy coevolution, particularly at high redshifts. One of my favorite, goals of our ancillary science is to use the data to search for the highest redshift supernova. At redshift 5 to 6, we may expect a detection rate of 1 per year per square degree, and that's pretty well matched to what we will observationally constrain compared to, different epochs of ground-based data at magnitudes roughly of 26. And also, for folks who work inside the Milky Way, the data will also be really useful for constraining ultra cool halo subdwarfs. We will be very sensitive to discover any subdwarfs down to magnitudes of 27 or so. And given the depth of our near infrared data and the filters, it will actually be very sensitive to constraining that population and segregating them from high redshift galaxies. And that can be really useful for understanding the low metallicity IMF and also the Milky Way disk scale height. So I think there will be some really interesting and unique discoveries across all astrophysics here. Okay, just to summarize, I won't belabor the point here, but ALMA has had really unique strides in high redshift science, many of which I think are unexpected or were unexpected when it first turned on. We in particular have, honed our interests towards the very early universe obscured galaxy population. That work is ongoing, but we think we have the first robust constraints beyond a redshift of 4. And on the JWST side, we cannot wait for data from Cosmos Webb to come in. That will be a tremendous legacy data set, not only for understanding massive galaxies on very large scales of the universe, but also for all areas of astrophysics from redshift 0 to 11. So with that, I'll stop here and take any questions.
Fantastic. Thanks very much, Caitlin. So we have plenty of time for questions. I see there's one in the chat already from Robert, who says, maybe this is too naive a question, but how does one determine the masses of highly dusty ALMA galaxies?
Yeah, that's a great question. So it depends on what kind of mass you're after. A fairly straightforward measurement to make is the ISM mass. We can infer this from the Rayleigh-Jean's tail of dust emission. That scales pretty straightforwardly with flux density. And so we can constrain gas and dust directly that way. And another way that we aim to constrain masses of these systems is through kinematics. And so if we have a spectral line and, can measure its size, measure the spatial size of the source and the velocity profile pretty well, then we can constrain a dynamical mass, and that gives us the total mass within that given size. And so those two techniques are very crucial, particularly when you can't see any starlight to give you a reliable estimate of the stellar mass. We do our best to use stellar population synthesis to constrain stellar masses of these systems, but it's often highly uncertain given the lack of emission we see in the optical and near infrared.
So that one, just to clarify, that one galaxy you showed, the very massive one, that has kinematical measurements through
Yeah.
C plus or something? Okay.
Yeah. It wasn't C plus, it was a CO line, but yes.
Okay. All right, more questions.
We actually, we're waiting for our C plus data on that system as we speak. Yeah.
Okay. So maybe I'll ask a follow on while other people are typing. So this cumulative distribution function you showed, I think this was from Jorge's work, that favored didn't favor the dust-rich model so much. I'm wondering what, if any, assumptions have gone into this about the dust temperature. We talked about this a little bit earlier today.
Yeah.
And if that helps or hurts you, if you really like the dust-rich model and want that to remain viable.
Absolutely. Yeah, so it's very, there are degeneracies swept under the rug here. We tried our best to model all of those. I'll say that there have been, many papers that have claimed that the early universe is any dust emission that there is to see should be much hotter, should have much hotter temperatures than we measure at redshift 2 or so. So instead of like 30 Kelvin, maybe 60 Kelvin, 80 Kelvin. And that makes a big difference in terms of the flux densities that we would measure at 2 millimeters. If you take if we're assuming a 30 Kelvin model, but we really should be using a 60 Kelvin model, then the flux density, given that temperature difference, should fall substantially. So, if dust temperatures are much hotter, our data would imply that the universe is likely filled with many more dust-rich sources than our model has constrained. We assume no dust temperature evolution because we haven't seen very compelling evidence for that yet, despite some claims. And so we talk about that a little bit in these papers, what the implications are. But yes, the universe would have to be much more dust-rich if the temperatures of galaxies are much hotter at early times.
Yeah, that's very interesting. Thanks.
Yeah.
So I'm not seeing any other questions in the chat, so I'll ask one more. The Cosmos Webb survey, this is really exciting, and I'm wondering for the kind of follow-up program on Keck.
Yeah.
Is the idea long-term to cover the entire area of Cosmos Webb, or do you have to be choosy?
Yeah, we're having to be a little choosy. It's a little the goal is, yes, to cover the whole field. But of course, not every square inch of cosmos has these candidates already identified. We're in a little bit of a difficult place because we don't have the JWST data yet. So our survey is of galaxies that we already know about at these redshifts, candidates beyond a redshift of 6, and it is a Lyman-alpha detection experiment. So we're doing our best to design slit masts at positions in the field that have a high density of these candidates, and that is variable across the field. So, yes, our goals by the end of this program are to cover as much of the field as possible, but I'm sure it is naturally an area where we might have several passes and try to follow up with other instruments as well. To fill in missing gaps.
Great. So another question from Robert, who asks, what about cross-correlating JWST with HERA?
Yeah, so we talked about this a little bit earlier. The coverage, the area coverage is a little bit of a mismatch, I believe. And also, the declination of targets, if you're talking about like Southern Hemisphere, Cosmos is an equatorial field, but it is in the north by 2 degrees. So, I haven't, done a detailed comparison, but if it would be visible or feasible to, stack on deep JWST data, and I think that would be very interesting. Yeah. But in terms of like JWST deep fields, there's not much real estate that will be covered on the sky. We're by far the largest program, and we're 0.6 square degrees. It's not that much. Yeah.
Okay, thanks. So we have another question from Arnab, who asks, is there a follow-up deep observation of molecular lines in Cosmos Webb?
That's a great question. Yes, well, there are already a plethora of observations already there because it sits smack dab in the middle of the Cosmos survey. And so, there has been a lot of effort. I think something like 5% of the full field has already been covered in one type of ALMA observation or another. Not all molecular lines scans, of course. It's a potpourri of different data sets that cover it, and it's not kind of continuous. There will be, yes, efforts to follow up in molecular lines, different subsets of galaxies that we will detect with Cosmos Webb. We are already, planning and in the works to follow up some of our initial sources. We may have detected Lyman-alpha in with the WERLS program to try to confirm through for example, C+. That can be a way to really strengthen our identification of these as very high redshift galaxies. So all in the works, yeah.
Very cool. Okay, so we're coming up on the end of the hour. I don't see any more questions, so maybe we should wrap here. So thanks very much again for visiting us virtually, Caitlin. It was great to have you. It was a great talk. And so I hope everyone will join me in giving you a virtual round of applause. And I hope to see you in person in Montreal sometime in the not too distant future.